So for the next panel, we have Katarina Hatsioanu, Assistant Professor of Physics, Greg Hallinan, Professor of Astronomy and Director of the Owens Valley Radio Observatory. We have Mansi Kasliwal, Professor of Astronomy and Director of the Palomar Observatory, and Mike Landry, LIGO Hanford Observatory Head and birthday boy. So this discussion, oh, how did I miss that? And Elias, Assistant Professor of Theoretical Astrophysics, and not forgotten. So welcome, panelists. Astronomy with all the observatories in the world. Now, what's one of the most surprising things that you've learned about the universe in the past decade? Maybe it's something that in your work made you stop the task at hand and say, whoa, I didn't expect that. Anyone? Moments of awe and wonder.
I can start, right? So recent means very recent. So I can tell you what happened on August 18th of 2025. So LIGO has been, the LIGO-Virgo-Kagra collaboration has been fantastic, right? They always surprise us with new things. 2015 was binary black holes. 2017 was binary neutron stars, my personal favorite. 2019 was neutron star black holes. And then there wasn't all that much until 2025, August 18th, when there was a low latency alert of a sub-threshold signal that claimed that two teeny tiny neutron stars merged. So these are neutron stars below a solar mass. And of course, as astronomers, when something we don't understand happens, we drop everything we do and point our telescopes at it. So that's what we did at Palomar Observatory. And we found what looks, well, for the first few days looked like the event from 2017, and then evolved to look more like a supernova that we know and love, which is a stripped envelope supernova. So this thing looks like a supernova inside which the core actually possibly fissioned to form smaller neutron stars and merged. So we like to call it a candidate. The candidate part is important. A candidate super kilonova, because there's a kilonova buried inside a supernova. So believe it or not, right? I mean, that to me is the most recent new surprise, and to be proven, to be confirmed in the future, but just keeps us excited and on our toes and looking hard at everything that LIGO and Virgo and Kagra are telling us.
Awesome. Mike?
So, I mean, 1509-14 was absolutely the most wow moment that I've ever experienced scientifically. Probably everyone knows that story, so I won't spend much time on it. But we woke at 5:30 to email from Germany saying that could this be a real signal, or is it an injection? And so that became the focus of the day, was to figure out whether this was something that we're chasing, or was it just something we had injected ourselves. And pretty quickly, by 8:30 a.m. or so, it was clear, and we launched this rapid response process. For the first time ever, those are protocols that we kind of developed in Stan Whitcomb's detection committee, the most fun committee I've ever been on, or ever will be on. But so that was the first event. It's kind of, in some sense, nothing compares to that, but this event from this year, GW251010, which became the basis for the Hawking area law paper that Katarina was so influential on. What for me I had a different take on that, because that's not physics that I know or understand well. But that event was so similar to 1509-14. The masses were roughly the same. The distance was roughly the same, but the signal to noise, was not 29, but 80 now. 80, just this mind-blowingly loud gravitational wave event. And that really underscores why the people at the observatories, why Callum's group and the people at Caltech, why the instrumentalists at MIT focus on improving the instruments. So it was a whole host of things like better scattered light improvements that allowed to unveil what's going on at low frequencies, but also, Lee's contributions and the quantum squeezing efforts at MIT and the groups at the observatories that built the filter cavities and created this frequency-dependent quantum squeezing that exposed so much of particularly the low frequencies, to make the SNR so good and to allow for the analysis.
That is so exciting. Now, that was clearly a pivotal moment. Do you find yourself getting just as excited every time a new one happens, or is it kind of like, oh yeah, 2 black holes again?
So people have the habit of saying this sort of cynical, vanilla black hole, whatever. I don't think that's the reality of it, because the ensemble of those measurements makes you now have some statistics, and you start to understand statistically what's going on. Are these different populations? Are some capture objects versus are some most maybe born of binary systems? So I think that there's a certain, we're always hoping for something that's electromagnetically bright, like 1708-17, the binary neutron star merger, and clearly those rates are a little lower than we hoped or expected for, but we'll get one. We will.
Yeah, so I think this is the thing that for the last few months working on this particular detection was the thing I learned the most. There's no such thing as a vanilla black hole, and I'm even embarrassed we ever said these words. The fact that even a single one of these weird objects exists out there is astonishing. It breaks our understanding of everything else that happens in physics, in quantum mechanics, in thermodynamics. So the very fact that even a single one exists out there and we can observe them, how could we ever dare call them vanilla? What arrogance? But no, just working on this is it's every little moment was completely unexpected. We've been analyzing simulated signals. We fake signals and try to analyze them. And just for fun, we make them as loud as we dare dream, and you get very interesting measurements. But then you get an actual signal that is extremely loud, because the signal-to-noise ratio of 80, as Mike was saying, is 3-4 times louder than anything you've seen before. And we're saying, okay, fine, 3 to 4 times better. We can do some very cool stuff about it. But I think the thing that kept surprising us at every step of the way is that I think every time we did something with a signal, let's do a new test, let's do a new analysis, let's change the analysis a little bit. And it came back and it was still constantly surprising us. We sliced the signal in many ways. We threw away part of it just to analyze a small piece of it. And that small piece of it was louder than anything else we had ever seen. And every time we got one of these astonishing, hey, look at how loud this one cycle is. It's astonishing. That the team analyzing this kept talking to each other, saying, "Oh wow, look at that." For multiple examples throughout this month-long process of working on this one signal. So, yeah, it's just whenever we feel, and whenever the astronomers also feel, disheartened. Why are you shutting down the detector right now? Just keep observing. No, it pays off. It really does. At the end of the day, it does pay off.
Amazing.
I might kind of riff on something that Nancy talked about. That event a couple of months ago. So I'm a radio astronomer, and you get, of course, light across the spectrum when one of these events typically happens, if it involves one or more neutron stars. But in the radio, it usually comes a little bit later. So, Nancy has to run to her telescope. I can kind of, gently walk. And, there's not as much of a rush. And we did, in fact, trigger the radio telescope, collaborating with Nancy and others, and we did lots of observations. But in the last year, we've been building a new system. And the reason we built this new system is because there are predictions from theorists, including Elias, that there will be not just a late-time radio afterglow, but a prompt flash of radio waves just at the time of the merger. And we spent the last year building that system. As a graduate student, Nikita Kosakarov did all the development work, and it's now deployed. Very exciting, but then when this event actually happened, we had set our thresholds a little bit too low. So when LIGO gives an alert, there's usually probabilities of it being a neutron star and so on. That kind of helps inform astronomers how to prioritize the time. And as it happens, we had set a threshold a little bit too aggressively, and we missed the event. So rather than it being a revelation, it's a cautionary tale. Be more optimistic, set your thresholds lower.
I love it. Ilias, any awe-inspiring moments?
Well, one thing I want to point out, because we heard a lot about black holes, and we heard a bit about, maybe exotic neutron stars. But I think it's good to just also remind ourselves of, how exciting the neutron star merger in 2017 was. Because that really was a revolution, I think, both for gravitational wave science, nuclear physics, and also multi-messenger astrophysics, given just all the observations across all the bands that have been made. On a personal note, because you asked me what, was the most exciting thing where, we had to leave everything else that we were doing. It was that event. So at the time I was a graduate student in Germany, and everybody was saying, okay, black hole, gravitational waves from binary black holes have been discovered, but neutron stars, will that ever happen? When will it happen? In fact, the group I was working in, together with other groups in the country, was applying for large funding from the local government. And the government was saying, oh, but it's so unlikely that there will ever be any detection of a binary neutron star system. Why should we give you money? Right? And the cautionary tale of that was that 1 month after they made that decision, they actually discovered the merger of two neutron stars, with all the excitement and all the insights in physics that we can learn from that. And the exciting thing to me really is that, this event has connected so many different communities. You can ask the question, what is new exotic states of matter? What's fundamental physics that's going on inside the neutron star in addition to, what gravity is doing? You can ask, how is that producing light? Days or weeks or years after across the band with all the telescopes that you can then use to follow that up, or even make predictions, as Greg was saying, what haven't we seen yet? So definitely I hope that, over the course of LIGO, we'll see more of those events, and then we can test all of the predictions, and we have everything ready that our colleagues are putting together. And I think that will be very, very exciting, and it's a really nice future ahead, I think. That's it.
Amazing. So I'm sensing a pattern here. Things are totally unlikely to happen. Kip Thorne doesn't think there's anything to this LIGO idea. And yet we're surprised. What are the things, maybe now, 5 years ago, 10 years ago, that you or funders think, it's just too unlikely that we're actually going to see fruit from that you secretly, or maybe not so secretly, think could yield interesting results?
Well, I always think that I always look for is neutron stars, of course, but also for reasons that are a little bit technical for what I like thinking about. I like to see low mass neutron stars, the most low ones, like 1 solar mass. That would be amazing, because these are the best systems if you want to understand the nuclear matter inside neutron stars. Inside neutron stars, matter is so extreme, so complex, we don't really understand what it looks like and how it behaves. And almost counterintuitively, it's better if you have low mass neutron stars that are less dense to study them. So when Nancy called me that evening and saying, hey, is LIGO going to retract this? What is this? And I went on our analysis and I saw, the mass is what? Hold on. What is going on here? That was my, I guess, the latest neutron star wow moment, because I feel like every time I've been telling people, you know what, I want low mass neutron stars, 1.2, 1.1, 1 times the mass of the sun. Can I dream that small? And maybe, maybe.
Well, this is Los Angeles. There's a lot of pressure for skinny stars. All right, if you could only fund one new observatory, LIGO doesn't count. Would you choose space-based, ground-based? Would it be purely gravitational waves, some sort of electromagnetic hybrid? What would your ideal observatory be?
Things that are not already in the plans?
Sure. Or one more.
Okay.
Cosmic Explorer.
All right, fair enough. All right, we went from.
Well, actually, with apologies to the gravitational waves community, an optical observatory that can detect kilonova as far as LIGO will be able to in 5 years.
Yeah, so why limit to optical? We can do it in the infrared. So I think, one of the things we haven't seen, we've seen LIGO detect neutron star black hole mergers, but we haven't seen light from it. And one of the reasons why we haven't seen light from neutron star black hole mergers could be it's really red. So we need an infrared, powerful infrared observatory that I like to dream about. It is not funded. I mean, I have a little experiment in the lab right now, but it's called Cryoscope, and I want to build this in Antarctica. So if somebody wants to fund that, that would be fantastic. But it would be sort of the ultimate neutron star black hole detection machine, because it is so red, it is at 2.35 micron. The sky is so dark that we can detect neutron star black hole mergers out to 400 megaparsec, which is the next generation of gravitational wave interferometers.
That is so cool. Cryoscope? I mean, amazing.
It's so cold. It's too cold to
So
call it a
cool.
telescope. We're cooling the whole tube, so it's fully cryogenic. So calling it a telescope would not work, right? Because you're cooling the whole thing. So
What about other
it's
wavelengths, not just infrared? What about multispectral?
radio would be fantastic.
Radio?
I feel sort of self-serving here because I'm building a radio telescope. So it's sort of, yeah, so radio, I think that there's an issue we have across the entire spectrum of light, in that amazing event, as I was described, really transformed this entire field, and it was in our cosmic backyard. It was 40 megaparsecs, 130 million light years, which doesn't sound close, but it actually is. And what's happened in the interim is LIGO has just gotten more sensitive, right? It's marching forward, and we have a real problem with the telescopes that we used, just 8 years ago, in that they really struggled at that distance. We used the world's most powerful radio telescope at the time, and still really in many ways, the Very Large Array, and it was just about sensitive enough to be able to characterize what was a very important signal. It's how we understood and confirmed there was a relativistic jet produced during that merger, and tied that phenomenon to the merging of neutron stars directly. Now, again, LIGO has gotten much more sensitive, and if you want to have an optical or an infrared or a radio telescope, it needs to be 10 times more powerful, and they just don't really exist yet, and we're trying to catch up with LIGO in some sense. And we are building a project starting next year to build the world's most sensitive radio telescope. And it will survey the skies 1,000 times faster than the Very Large Array that was used a few years ago. And that's just about enough to see a LIGO event at the current range. And when LIGO comes back online in 2005, it'll be almost, we have to upgrade again. So the goal here is to keep up with LIGO.
Amazing. So we can hear the universe. We can see some of the universe. When will we be able to smell and taste the universe? And how is that going to give us a complete picture?
Yes, if you want to
You need particles.
Yeah,
right?
neutrinos.
Then really you need
and
neutrinos.
cosmic
Then I
rays.
think that's the way to do it.
Antarctica. I think we can find some neutrinos
Exactly.
And LIGO paved the way, but there are other, in the same way that we have light in the optical and infrared and X-rays and radio, you also have other wavelengths of gravitational wave that we want to open up the universe to. And there was a lot of discoveries there that we will see when we begin to expand in wavelength. So that's not the same as as smelling or tasting, but I think it'll be a lot of discoveries come in that direction.
So just to add on Cosmic Explorer as a future gravitational wave detector, something that could come online mid-2030s, so 10 times longer arms, so 10 times more sensitive. That also gives you louder events that are close. So even within that bubble that electromagnetic observatories see, will detect more of those, right? So that helps in all cases.
But definitively, we'll be able to smell the universe when we get the next galactic supernova. Because I'm interpreting smelling the universe as particles and neutrinos. And at that point, we will all be able to see it with our own eyes, probably in the sky, as long as it's this side of the galaxy. and gravitational wave detectors will find it, and every telescope and pair of eyeballs in the world will be able to see it, and we'll get neutrinos from it as well. And it will happen at some point. Supernova happen in our galaxy once every 100 years, is that right? The last one was 300 years ago. That's not how statistics work. Don't get excited. But it will happen at some point.
It could be tonight.
It could have already happened. Check your phones.
And we may have missed it because, we didn't have the telescopes to see, if it, like you said, if it's on this side of the galaxy or if it's not in the galactic plane, it'll be very bright. But if it's actually the far side of the galaxy behind all the dust, previously we would have missed it if it was a century ago. Now, of course, we won't, because we'll see in other wavelengths and we'll detect the neutrinos. And of course, very importantly, we will detect the gravitational waves, which will be exciting.
I think one thing also to add is in terms of, we heard a bit about space-based gravitational waves also. I think merging supermassive black hole binaries I think are also very exciting, because then we don't just get a flavor of gravity, we also get a flavor of all the matter around. And so you can get basically super multi-messenger events. The challenge there is, of course, the predictions, I think, are not yet where they have to be to really say even with what telescope to look at. And then, most promising would be the X-ray, but there our capabilities over the next 10 years, I think, are a bit uncertain compared to that in, I think, other countries. So thinking a little bit about what is needed both on the theory and I think on the observation side for those coming up in maybe 2035 or so, I think might be exciting too.
Very exciting. So now we have different ways of sensing the universe. How is that data, fused together? Do you think it's more than the sum of its parts? That's the first part of the question. And the second part is, how is artificial intelligence and advancements in machine learning helping to expedite or, really bring some of these insights out of all the data that we've been able to gather?
So those data are definitely more than the sum of their parts, right? If you just take a simple measurement that was done from the neutron star, binary neutron star, 170817, you had gravitational waves detected at Earth, and then 1.7 seconds after the approximate merger at the top of the chirp of that 100-second long signal, 1.7 seconds later you had a burst of gamma rays in Fermi's space-based detector, a NASA detector. And so that's the first direct measurement of the speed of gravity. It's 130 million light years. You basically can do it in your head, just 1.7 seconds divided by that number. You get the rough delta between the speed of light and the speed of gravity. That's the max, right? And it's certainly less than that. Probably that fact that the light is arriving later is a function of how that jet of gamma rays sets up and how long it takes to get out, because it's smacking into this incredibly dense matter on the way out. So that puts a limit on. So that's already, just a very simple analysis. The actual analysis is more complicated than that, but the point is that you get that only out of having multi-messenger sources there.
So cool. Okay, so we've got gravitational waves out there. They're bouncing all over the place. Do we ever see them crashing together? Do we see, phase interference constructively or destructively? Like what happens?
Exactly what you're describing will happen. They will crash
What
together.
happens to space-time when gravitational waves either connect or cancel each other out?
I can give you a theoretical answer.
Oh, please do.
and some computational prediction. So together with one of the grad students, one of the things I've been excited about in the past month, we actually asked exactly that question. Namely, can you have, from the interaction of gravitational waves, turbulence? Meaning just, if you have, clouds merging, or if you have in the solar wind specifically processes that sort of, have interacting waves that then cascade to smaller scales, what does it actually look like? And so one thing that we were able to show mathematically, that general relativity, if interpreted in the right way, has almost the same description as the turbulent structure of the solar wind. Meaning that when you have collisions of counterpropagating waves with the right polarization content, they actually split up, go to higher frequencies, and then form a turbulent cascade in exactly the same way. And we tested it out in a computer. It seems to work out. So, the math works out anyway, but the simulation looks good too. So I think, yes, so there is a prediction we can make, but we have to think of it.
Okay, now explain that to my 7-year-old son.
We do have some context here in the sense that, LIGO, of course, detects the gravitational waves from emerging black holes and neutron stars. We now, following in the footsteps of LIGO, we have radio telescopes can actually use the measurements of spinning neutron stars, zombie stars, the leftovers of supernovae that are spinning extremely quickly, and use the pulses from those stars to measure the gravitational waves from binary supermassive black holes. And that first detection only happened in the last year or so. But they didn't find an individual detection, as is the case for LIGO. What they found was a stochastic background. That is the sum of the signals from all of the supermassive black hole binaries in our universe. So we already have an example measurement just like what you're describing.
And there's a possibility you might see such a thing from the ground-based detectors in the 5th observation run. We're finishing up our 4th observation run mid-November, and then there's some period where we're installing components to make the detectors more sensitive. And in the 5th observation run, some people indicate that, well, you're getting to a point where we think that the sum of all binary black hole mergers in the universe arriving at the detectors, arriving at Earth, will give that same kind of stochastic source.
Okay, so it's 2035. We're celebrating, we're just doing the same event, exact same. Kip's giving an amazing talk. David writes he's still here. Sorry? It's Mike's birthday again.
Made it.
40 years old.
I don't know how that works.
What's LIGO's next gift to humanity? That student up there is working at LIGO, by the way. It's mid-career.
There's so many questions that we need to understand. I think we heard earlier on from Kip and Rana about some of the untold discoveries that still lie out there. And that includes, for example, more nearby supernovae and different types of gravitational waves. But there's so much we have yet to resolve from the merger of neutron stars, as an example. We got that little taste from GW251010, and it really gave us some evidence that, this is where the heavy elements of the universe are created, but we don't have that definitive answer, actually. And this is more Monsi's territory to maybe elaborate on this, but I think that's something that would be very important to understand. The role in the creation of the heavy elements that we, getting a definitive answer, is this the right progenitor pathway for that process?
So I want us to have 100 neutron star mergers. So you can ask the question about, is it going to be a vanilla one or not?
It's going to be chocolate, strawberry, vanilla. Okay, so drill down on that concept one more level. Let's say we do confirm it. What does that mean?
It's half the elements in the periodic table that are heavier than iron that are synthesized in neutron star mergers, right? And we have one example, right, from August 17th, 2017, where we have definitive proof that half of a periodic table was made, right? It's 2025. We should be able to do better than that, right? I mean, it's not clear, and there's a little bit of data that suggests that the heaviest of the heavy elements were made. People still debate it. Is this the only way by which heavy elements are made? Do all the heavy elements get made this way? Are there other pathways to producing this? Can we just explain the building blocks that we see around us? We use all these elements every day in our life. We're made up of many of these elements. Can we just explain where they were made? It's a very, very, I think, basic question that even little children, I think, can ask and want to know the answer to.
Are we all wearing a little bit of neutron star
dust? Yeah. But I think we should be able to do better in answering that question 10 years from now. So I think that would be a great gift, right? Just knowing where we come from, right? Where are the elements you and I made up of? Where do they come from? More definitively than a few little hints.
Our origin story. Okay, I think with that, let's open it up to Q&A from the audience. Kip.
I haven't heard you say anything about seeing gravitational waves from supernovae, from cosmic streams, from turbulence in the very early universe. There are all kinds of speculations that have a fair degree of plausibility that we've not seen yet. And I'd just like your personal impressions on these other sources that I used to talk about vigorously many years ago, that you're not talking about.
So the question was, we haven't seen novae, we haven't seen cosmic strings.
We haven't seen waves from turbulence in the very early universe.
Turbulence in the very early universe. What do you think?
We haven't seen them, but not for lack of trying, right? We scrutinize the best of our ability every single data point that we get. Okay, that was an exaggeration. Some are not good quality enough, but most of them we do our best to make use of every single information coming out of the detector. We analyze everything for supernova. We analyze everything for cosmic strings. If they are within our capabilities, within the detector sensitivity to get them, we will get them. We don't have to compromise on any of these aspects. The same thing with early universe processes. We analyze all the data for that aspect as well. But I think Greg was saying this prospect is becoming theoretically a little bit more distant because that signal will probably be buried by the astrophysical signal from the black holes. I think it was Mike maybe who was saying that, but the stochastic background that we will also see in LIGO. And probably the first stochastic background that LIGO will see will be from black holes and neutron stars. Any early universe signal will probably be buried underneath it. So we're not saying anything because we haven't seen them yet, but that doesn't mean that there aren't computing nodes currently right now searching for those things exactly.
I think it's worth exuding some enthusiasm for this.
Oh, yeah.
Oh, yeah.
So in 10 years, they're going to be old hat, is what you're saying.
I think they're one, the serendipity aspect, the unconstrained and unknown is the real reason why we have to keep driving forward with sensitivity with LIGO into that next generation, because, if LIGO had not put the huge effort in to be ready, when it was ready in the Observing Run 3, we may never have seen neutron star merger. We may still be speculating about that observation. And the new populations is always going to be one of, if not the biggest reason why we have to keep forging forward.
And I would add to that, I would love to see more efforts to actually understand supernovae, where it's not axisymmetry that's giving you gravitational waves, but supernovae where is it actually possible that the core fissions or the accretion disk fragments to form subsolar mass neutron stars, is that a real thing? And if you can actually get some templates for that you search for and see these little neutron stars merge, maybe followed by a neutron star black hole merging, I think just sort of completely thinking out of the box for templates to search the gravitational wave data for could be eye-opening, right? It could be a gamble. You could end up with not seeing anything, but it could, if you see it, it would be very fundamental to, I think, the textbook on compact objects.
And we probably, it's 10 years. We probably have a better than even odds, I would think, based on LIGO's track record of seeing something that nobody expected. That could be just, change the game.
One thing to also say, now we also have both the computational and the theoretical capabilities of actually providing you with a template, right? We have developed all of these tools to actually study the dynamics of accretion disks, simulate gravity in that regime. So, we're well capable of doing this now.
So the LSC is really big, the LIGO Scientific Collaboration, and there's a host of different analyses that are going for all these more speculative types of sources, and at the extreme, like you're referring to, Greg. So one, for example, is axion production through superradiance at black holes as they spin down after merging. And that's a really exotic source, and if you talk to people about, who are writing those analyses, do they really think those are likely sources? I don't think they're convinced that the universe produces these, but they really want to check, and they make excellent codes to do so. And the detectors get more and more sensitive, so at some point you can expose at least upper limits for those. Maybe someday from one of these speculative sources, that's what we'll be discussing on my birthday.
But ultimately, we are constantly searching for unexpected things, and those analyses are constantly finding things. They're just black holes. All the black holes that we have detected, we would have been able to at least detect them, not all of them. The majority of them, we would have been able to detect them, even if we didn't know where they were coming from. We wouldn't have been able to tell much about them. This is where the real use of all this modeling comes in. It really helps us to understand the properties of those sources. But we would have been, if a cosmic string signal comes tomorrow and it is loud enough to be detected, we will detect it.
So it's basically 2014. We don't know how many black hole mergers there are. We've got good estimates, and we've got to keep trying.
Always darkest before the dawn. All right, another question. Yes?
So what does a template for a cosmic string look like?
It will look like a blip, pretty much. Yeah, so stuff that we are already very, very good at looking for. However, if you don't have this template, you won't be able to say much more beyond some very basic things about it. The same.
Frequency or it swims through?
It depends on the kind of cosmic string. There are different types.
All right, another question. Yes?
So when you mentioned the gravitational wave background, that was kind of reminding me of the cosmic wave background, right? What can this stochastic variability tell us about the universe?
Sorry, can you say the end of that again, please?
What can the stochastic background tell us about the early universe?
What can the stochastic background tell us about the early universe? Does Siri know?
Yeah, Siri was trying to answer there. Well, so this generation of detectors is not likely to see that, right? It's several orders of magnitude down. So it's definitely a hard source. But I mean, for me, that stochastic gravitational wave source occurring very, very early in the universe. You know, the light we get is 380,000 years after the Big Bang. There's all these epochs of physics that are available, should be available through stochastic gravitational waves, you know, before that. So it's the reason why you do this kind of experiment, turn on a new gravitational wave detector. The thing is, we don't think we'll get to it with this generation. Hopeful for future generations. I'm actually interested, Katerina, what do you think of the prospect for subtraction of binary black hole, the sum of all binary black hole mergers in the LIGO noise band? How far down can we go with that process?
For what kind of detector? It depends on what detector we're talking about.
For, say, a Cosmic Explorer detector, which is sort of, you know, technically similar to LIGO.
Yeah, so Cosmic Explorer is the instrument that has 10 times the size of LIGO, which means it is 10 times better, which means it can see every single binary black hole merging in this mass range, less than 100 solar masses, anywhere in the universe. Which is quite astonishing to just think about it. You know, in 20 years, you go from the first, 30 years maybe, you go from the first detection to the edge of the universe. But binary black holes, if you can detect all of them, there aren't that many of them, enough to ruin the stochastic background. Just as a rough estimate, there's 2 black holes merging somewhere in the universe every about 3 to 4 minutes. And we observe the signals for less than a second. So, you know, they happen and they're done, and then you have some quiet data without black holes. So if you convince yourself that the detector is good enough that you're detecting every single one of them, you can get to what's beneath them with Cosmic Explorer.
It's not somewhat unrelated to the background, but generally speaking, we can also use LIGO events to understand the universe in a very different way, and that is because they're a way to independently measure how far away something is. It's really, really hard to measure distance in astrophysics, and a lot of the journey we've been on for the last century is just figuring out how big the universe really is. And in astronomy, we've managed to do this using something called the standard candle. So we can measure a nearby star and say use parallax to see how far away it is geometrically, and then calibrate variable stars who pulse with a certain period, depending how bright they are, and so on. And then in the last 2 decades, we've been using supernovae, a certain class of supernovae, as a standard candle, and that's how we discovered that there was something called dark energy, and that has been transformative for astrophysics. Well, it turns out that you can use, instead of a standard candle, you can use a standard siren, and that is the exact kind of events we're talking about today. And in some cases, you can use the combination of light to be able to improve that measurement, and that's what we actually did for that event, GW251010. We were able to measure geometrically how fast the radio emission was traveling and determine the viewing angle to the event to better constrain how far away it was and get a measurement. The real fundamental metric here is something called the Hubble constant, and that's just essentially a yardstick for the universe. And there's a real big controversy right now in cosmology and in our understanding of how the universe evolved. There is a disconnect between the constraints on that metric that you see in cosmic microwave background data, which is sort of early universe data, and what you measure by measuring nearby supernovae. And it may be that we can use hundreds and thousands of LIGO events to have a separate way to resolve that outstanding, huge open question.
Do we have time for 1 or 2 more questions? Yeah, over here.
What other frequencies in the gravitational wave spectrum are you most excited to get data from?
So the question is, what other frequencies are you most excited to get data from?
Katerina should answer that.
Yeah, well, okay. So what frequencies we will get data from is different than what frequencies you want to get data from, right? But we know that we will get data from outside of LIGO, the audible band. If you go down to millihertz, you will, in 2035, a little bit after 2035, so maybe for the 30-year anniversary, we'll be talking about that. But we will get data from LISA, the space-based mission, and in the nanohertz regime, we are already getting data, and we'll get a lot more, thanks to Greg in a few years, data from supermassive black holes emitting nanohertz gravitational waves. So this will happen. We'll be talking about in future anniversaries. What will be really also nice is to get data between LISA and LIGO, so the decihertz regime, because especially if black holes, we don't know exactly how the black holes that we're detecting form. But there's sort of 2 options. One option is that they come from 2 stars that have spent their entire lives together. The binary started from really far apart and has slowly been spiraling to collision. Or they formed very recently in a very dense environment. And if you get data from the decihertz regime, you might actually be observing them forming, observing the binaries as they form, as the 2 black holes capture each other, which would be really cool. There are some concepts for those detectors, and now I'm thinking that should have been my answer for what I would have liked funded. Optical telescopes are also good. Maybe I'll stick to that answer. But if I had another choice, I would say decihertz gravitational wave detectors and data.
All right. 2 more questions. Yes.
Gravitational waves theoretically provide any insight into the dark matter structure of the universe?
So the question is, can gravitational waves provide any insight into the dark, did you say energy? Dark matter structure of the universe?
The problem is we don't really know what dark matter is. So there are types of dark matter, types of energy regimes of where a dark matter particle could operate that are exactly what LIGO could do. If the mass of the particle is such that essentially its size, if you think of it in terms of wavelength, is comparable to the black hole, the particle would interact with the black hole, so you can do something. Of course, maybe dark matter particle is nowhere near the size of 30 solar mass black holes, so there's much we can do, but yes, absolutely. If you have to search for everything, and of course we do search for that option as well.
What about polarization constraints? Since Rana said we may have another LIGO, if you could have propagation effects from the gravitational wave passing through certain types of dark matter.
So polarization constraints, there's several things, lots of things you can do. So if the system itself contains polarization states that are not what you would expect, that would be a test of general relativity. If gravity produces polarizations that are not your standard ones, then that is a immediate test of gravity. But you can also check how those polarizations propagate towards you at the moment they get emitted and after they reach Earth, how they travel towards you and how they interact as they travel. Some might be slowing down, some might be speeding up. So that is another aspect, right?
All right, one more question. Yes?
Hi. So basically, kind of like the same question, but instead of dark matter, like if there has been any new insights regarding the expansion of the universe because of the gravitational waves research.
So the binary neutron star event itself, 1708-17, allowed for a Hubble constant measurement. And that was just one event, but you had the sky location, you had the exact galaxy, NGC 4993, discovered by Herschel in the 1700s and known to be 130 million light years away. So having that allows you to make a Hubble measurement. You've got a luminosity distance that came from gravitational waves, and then you've got, you know, a reddening of the galaxy from the host galaxy, and that allows you to make this measurement. But the analysis is quite broad, so it encompasses both the measurements that are in tension from the cosmic microwave background and from, you know, the recession of supernovae. And so it doesn't resolve this dispute in any way. You need an ensemble of measurements from gravitational waves. You can also do more with the black holes, provided you know what galaxies they reside in, and you don't, but you can do a statistical analysis based on galaxy mapping. And so together, these direct measurements that come from, you know, binary neutron stars and the statistical association of black hole mergers with galaxy catalogs allows you to start to carve out this space, and we'll see where it ends up. We need more data for that. So I think the collaboration has learned how to do those analyses now. We get more data, we make more of these analyses and start to push on that discrepancy.
Great, guys. Any final thoughts, questions you wished you were asked before we conclude the panel? No? Awesome. Thank you so much.
Thank you.